introducing. So yeah, so I've already been introduced. This is a topic of my PhD. So as I said, it's between thinking about how these submesoscale eddies and sea ice could interact, and what could be the importance of the submesoscale eddies for sea ice. So just a quick background on submesoscale eddies to begin, which hopefully isn't too much of a repetition. So these submesoscale eddies in the ocean are on the time scales of about days to weeks and length scales of meters to kilometers. And this means they're subgrid scale in most global climate models. And so their study is more limited to high resolution regional models. For example, there's an example on the right top here of simulation of them. And they're often confined to or mostly found or observed, for example, in the mixed layer, the top layer of the ocean, and their length scale is also sort of limited by the depth of the mixed layer. And then dynamically, they kind of tend to bridge between the larger balanced scales, like the mesoscales, and the smaller unbalanced scales, and tend to have Rossby numbers of order 1. So in terms of that, why they're interesting for the climate, or the main sort of climate interest for them is, for example, vertical fluxes. So they could, there have been lots of studies which have looked at how these eddies could flux nutrients, for example, from the deeper ocean into the mixed layer, and therefore be related to the growth of phytoplankton, because the top layer of the ocean is where it's sunny, so that leads to the growth. And then, so not just nutrient fluxes, but also buoyancy fluxes between the subsurface ocean and the mixed layer can re-stratify the upper ocean and therefore set the depth of the mixed layer. And the stratification. And then so I'm going to be talking obviously about their impacts in polar regions. So this could be like sea ice melt rates, for example. So yeah, the next slide goes a bit more into these studies of these submesoscale eddies in polar regions. So there's been a few observational campaigns. For example, in the Southern Ocean, this is, sorry, on the right here you have like a satellite image. So this is, you can see maybe the traces of these eddies at the edge of the sea ice, depicted by the sea ice. But then there's also been some campaigns which have actually gone into the Southern Ocean where the sea ice has retreated, or left over lots of fresh water, which leads to like strong submesoscale fronts in the mixed layer because of this freshwater gradients. So yeah, those have been like actually measured in situ, and then there's also been modeling studies into possible different impacts of the eddies and with sea ice. So for example, Horvath looked at like different melt, how the eddies can influence lateral melt rates. So because the melt rate of like sea ice flows, for example, can depend on how many the diameter of the sea ice flows or how many there are, then these eddies actually bring warm water and melt the ice, so that can have a big impact on those melt rates. And then in addition, other effects could be impacting like the stratification, that's been looked at, and also mechanically then eddies can like trap the flows and move them around as well, between like warm cores or cold cores. And then into looking further into the future as global warming takes place, the prevalence of these eddies, because they tend to be more suppressed by the sea ice, whereas more present where there's in the marginal ice zones, or where the ice is broken up, then the prevalence of them could increase in the future. So their importance could potentially increase as well. So now I'm going to go more into my work, so what I've been doing in the last few years. So I've been looking at these MLEs and polar conditions, and then building on previous work, so trying to understand what could be the impact of these eddies on air sea fluxes and sea ice, and then also thinking about things like seasonality. So how could the season impact like the growth of the eddies, or the impacts of the eddies, and also location, and then also thinking about how a pre-existing parameterisation of mixed-layer eddies, which was developed by Fox-Kemper, may behave in the presence of sea ice. So I'm using a modelling study. So this is using the MITgcm, and the way that I measure the eddy impact would be to compare a 3D simulation against a 2D simulation with no eddies. So the setup of the model is to have open ocean in the south, and then the north is covered in sea ice of 1 meter thick. So it's the open ocean, the south is like totally ice free initially, and it's focusing on thermodynamic effects, so there's no wind, and then in the 3D model there's perturbations in the temperature field, which lead to the development of the eddies, and the resolution is 250 meters. And I run it for about the length of a season approximately. So I've got 4 different experiments that I've looked at. So I've looked at Arctic, summer and winter, typical conditions, and then also Antarctic, but mostly I'm just going to talk about Arctic, and I'm going to start with summer. But these just show the different profiles that I've used, and for salinity and temperature and density. In general, Antarctic tends to be more weakly stratified. And then obviously but within my experience, the initial mixed layer depths are different between summer and winter, again, sort of in accordance with what the profile, those profiles show, and typical conditions. So these are, we start with the Arctic summer. So there's the shortwave warming. So initially you have uniform temperature within open and ice covered ocean, but as you start the model, the shortwave forcing leads to faster warming in the open ocean, which you can see here, than in the ice covered ocean, which at least the surface will remain a freezing point, but the ice will melt. So this leads to a lateral density gradient between the open ice covered ocean, which brings about a jet along the ice edge, which eventually meanders and forms eddies. So these developed without simulation. So this is a sort of comparison of, in this Arctic summer experiment, the 3D and the 2D model. So these are density slices, like snapshots. And you can see here, so if you look at the top, then this is the freshwater melt. So you can see that right at the very surface. Then underneath that, you have warming in the open ocean. So they're basically in the open ocean, it's more, it's less dense beneath the surface. But there's a reversal of this density gradient from the freshwater dominated at the surface to temperature dominated below. And this basically illustrates just how the eddies have acted to slope these isopycnals, and in the 2D the fronts remain sharper. So one thing I looked at was the heat budgets between open and ice covered ocean. So I split the domain just at the ice, at the location of the original ice edge, and then looked at the heat budgets into these two regions. So for the open ocean, the solid lines are the 3D model, whereas the dashed lines are the 2D model. So the air sea heat flux, which is the blue line, you see it decreases over time, and that's because of the rising temperature of the open ocean. The red line is the meridional heat transport out, well, in this case, it's out of the open ocean. So it's negative into the ice-covered ocean. So you can see that this is strongly impacted by the presence of eddies and is greatly increased. So that leads to a slower warming of the open ocean. So there's an impact to the open ocean, but because the air sea heat fluxes are large compared to this meridional heat flux, the air sea heat fluxes dominate, whereas in the ice covered ocean heat budget, this meridional heat flux due to the eddies dominates the heat budget because the air sea heat fluxes are very small. So overall, this meridional heat transport due to the presence of eddies is tripled into the ice-covered ocean with respect to when eddies are not present on average over the simulation. And this leads to a doubling of the heat storage in the mixed layer. So then this has subsequent impacts for the sea ice and air sea heat fluxes. So here, this is the Hofmüller plot. So it's a zonal mean air sea heat flux against time on the x-axis. So as we go further into simulation, if we look in the southern region, then there's basically warmer colors are maintained for longer in the 3D, and that's those air sea heat fluxes being maintained higher for longer where eddies are present. And in addition, the blue flux, which is associated with melting in the northern region, you can see is more widespread within 3D model, and this leads to overall 20% more shortwave radiation reaching this ice-covered ocean compared to with no eddies. And then if we look directly at the sea ice volume, these plots show how over time the sea ice is greatly decreased. There's a 10% reduction with eddies, so the solid line again, by the end of the simulation compared to without them. But this is slightly dependent. So you can imagine that eddies are developed and they don't necessarily reach the edge of the domain of my model by the end of the simulation. So if we look just at on the right here, the region in which the eddies extend to. So this is a zonal mean of the sea ice at the end of the simulation. So you can see here, this is where the eddies basically melted more ice. So if you only include that region, then it's a greater impact of 17%. So yeah, just to show those differences. So I also looked at the actual overturning in this model, and so I've used the residual mean framework, which has looks at the overturnings of the water masses. So if you look at the residual stream function in the middle for the 3D model here, which is the main stream function of interest, So this acts to move the water masses, rise the warm water on the open ocean or more buoyant side, and sink it under the ice. So it's a clockwise cell. And we can see that the eddy component of this total overturning, which is given on the right here, is basically dominates this overturning. And if we compare this overturning to in the 2D model, you can see that there's basically a factor of 3 difference between the overturning in the 2D model compared to the 3D, and that scales directly with the heat budgets. So we can see just another illustration essentially of how these eddies are acting to overturn and move this water into the northern region. Okay, so that was talking about the Arctic summer and what I saw in those simulations. And as I said, I also looked into what happens under winter conditions. So that means I essentially started the model run again, and this time used different initial profiles and different forcings. So again, you start from horizontally uniform temperature and salinity in the mixed layer, and you have a deeper mixed layer depth than in the summer, of 100 meters in this simulation. And in this simulation, the ocean cools. So this leads to ice formation as opposed to ice melt. And these ice formation rates are they're faster in the open ocean because there's no ice there already. So essentially, where there's no ice, it forms quicker. And this brings about a salinity-driven meridional density gradient in this simulation. So because there's more ice forming faster in the open ocean leads to quicker brine rejection, and so there's high salinities in the open ocean. Whereas the temperature gradient is constrained by the regions being at freezing point, and in this simulation, the mixed layer deepens over time and is unstable. So you can see that these profiles, these density profiles on the right here, compared to the summer ones, are basically unstratified within the mixed layer. And this mixed layer depth deepens over time. So hopefully you've got in your minds the winter simulation now. So I also looked at, I did basically the similar analysis for both simulations. So I've also looked at heat budgets in winter. But as I've said, because both regions are at freezing point, then the heat budget effects are smaller in winter because there's not as much heat transport or meridional heat transport that takes place, for example, because of those temperatures, whereas freshwater transport, salinity transport would be higher. But overall, the eddies still have an order 1 impact on these heat budgets, but this doesn't really lead to a change in the sea ice overall, because there's a sort of almost competing effect, it appears, between meridional heat transport and also different vertical heat transports between 3D and 2D models. But overall, there's very little difference in total rates of ice formation between 3D and 2D in winter. But in the winter, the main impact that I saw within these simulations of the eddies, or the main interesting effect, seemed to be the difference in the mixed layer depth, or the development of the mixed layer as the simulation goes on. So this shows the eddy overturning in the winter. So it's negative in this case. So this residual stream function is negative, and that's the opposite direction to the summer because the meridional density gradient is the opposite sign, and it's also stronger than in the summer, which is possibly because the mixed layer depth is deeper, which has been shown in parameterizations, for example, of mixed layer eddies, that the stream function could be proportional to mixed layer depth or mixed layer depth squared. So yeah, this overturning by the eddies leads to positive vertical eddy buoyancy flux, which is illustrated here, and the black lines are the salinity contours. So this is fluxes buoyancy upwards, and this means that the mixed layer depth is basically more shallow in the 3D simulation with eddies than in 2D simulation. So the eddies basically make the mixed layer depth deepening about 80% weaker than without them. And you can see here in this graph C that this basically a 3D, 2D difference of the mixed layer depth. The meridional variation is shown, and you can see that basically increases over time as eddies grow and reach the extent of the domain. So just a touch, I'm not going to go into it too much, but just to touch on the Antarctic simulations as well. So I also just thought, okay, so could there be any dependence on the location? So for these different initial profiles, might anything different happen in these simulations? So in the Antarctic, using Antarctic profiles, which I showed at the beginning as like more weakly stratified, I saw very little difference between this Antarctic simulation and the Arctic one in the summer. Basically, most of the analysis looked really similar. And I think the reason for this could be that in the summer, because the subsurface ocean is not really accessed, because the forcing acts essentially reinforce stratification. For example, the freshwater forcing due to ice melt. So this subsurface, which made stratification, which may depend between location, is not really accessed by the mixed layer eddies. Whereas in winter, because the mixed layer depth deepens, and this happens a lot quicker in the Antarctic simulation, which is more weakly stratified. So there are a few more differences between Arctic and Antarctic winter simulations. For example, this overturning by eddies is deeper and slightly weaker. The meridional density gradients are weaker. But the main impacts I've seen, like the restratification, are also reasonably similar between these different locations. So essentially found quite strong dependence between seasons, but low dependence between locations, at least within this model. So the last thing I'd like to talk about would be the Fox-Kemper mixed layer eddy parameterization, and whether using this parameterization within models with sea ice could reproduce some of these effects that I've demonstrated. So this parameterization comes in the form of a overturning stream function, which I'm going to point out a few factors here which are most maybe important or noticeable. So the H is a mixed layer depth. So I've already talked about perhaps the dependence of overturning on mixed layer depth. And also the grad B here is the mixed layer averaged lateral buoyancy gradient. And then F is Coriolis frequency. And then this factor at the front here is essentially, so delta S is the resolution of the model in which this parameterization is being used. And this is designed to basically account for manifestation of weaker density gradients at coarser resolutions. Whereas the, and then the factor, the LF factor, is also to account for how the scale, so it's essentially this LF is like the front width of these mixed layer fronts, so how that could vary with latitude, for example. So that's designed to account for how those eddies could actually vary in scale in different places. And as a result of this factor, it means that this parameterized stream function is smaller or has less impact in high resolution models, which will be better or will resolve more eddies anyway, basically. So that's interesting feature of it. So what I have used this parameterization is I used it in my 2D setups, which have no zonal variation, looked at different resolutions, and also I looked at using different choices for the mixed layer depth H, because there's a couple of different choices that you could use. So I used this parameterization in my summer simulations. So this here is just what I saw in the 3D module, the 3D eddy overturning. And so I said that I could use different values for this H mixed layer depth. So this could be, for example, the default mixed layer depth, which is based on like a step change in density as you go deeper into the ocean, or another possibility is using the KPP boundary layer depth, which is obviously different to using a mixed layer depth because it's only present when you have mixing within the mixed layer. So for example, in the presence of winds or buoyancy loss at the surface. So I initially used this, tried using this KBP length and the mixed layer depth within this parameterization at different resolutions. And the result of that is what you see in the left column here. And you can see this doesn't represent the eddy overturning that I've seen in the 3D. That's because in the summer you have like a freshwater melt, so it's very highly stratified right at the surface, whereas this main bulk eddy overturning that I've seen is because of the more subsurface, but still within the initial mixed layer temperature gradient. So that's just not captured by using these sort of standard value of mixed layer depth. So I tried manipulating a little bit, maybe the stream function, or just changing it to not include the surface layer within the parameterization. So skip out this very strong comparatively salinity gradient at the surface. And that means the parameterization just includes the temperature gradient, and you can see that this actually massively improves the accuracy of this parameterization. And you can see the impact of changing resolution, so resolution gets coarser going down this column. You see it gets stronger and wider as the resolution gets coarser. But overall, I looked at also, whether these 2D resolutions and 9 kilometer reproduce, for example, like meridional heat transport by eddies, and still seems better at the coarse resolutions, but still slightly underestimated at 9 kilometers, for example. So that was the summer. Another thing to notice is that as the parameterization, you can see these fronts here at the ice, like located at the ice edge, and they get coarser with, they get wider with coarser resolution, and that actually means this stream function becomes wider as well. So again, the width of it is actually most well represented by 9 kilometers. So then in these winter simulations, I also tested the parameterization, and I talked about using different values for H. So I tried using also the default mixed layer depth in winter. And this is because there's no strong stratification at the surface, just using this default mixed layer depth quite well reproduces the winter overturning, and also impacts like the reduction to mixed layer depth. So yeah, the parameterization performed reasonably well in winter, but again, the impacts are really only well produced at the 9 kilometers. And then the difference, so there's difference between these two columns here on the right, is using mixed layer depth or KPP mixing length. Because mixed layer depth tends to be deeper than this mixing length, then that's why this stream function is actually stronger using the mixed layer depth. So yeah, sorry, these color bars aren't actually the same between this 3D and these 2D ones, but these seems to sort of almost actually overestimate this overturning by Eddy's using this default layer depth. Okay, I think I'm going to stop there. So I'll just give my summary. So I've talked first about how these submesoscale eddies could have order 1 impact on climate variables like heat storage, lateral heat transport, air-sea exchange, and mixed layer depth. This could depend highly on the season, but not necessarily to the location. In summer, the main impacts were increasing shortwave radiation and inducing a kind of positive feedback between ice melt and shortwave radiation. And in winter, eddies could reduce the mixed layer depth by up to 80%. And then this Fox-Kemper parameterization performs reasonably in winter, whereas in summer, more sort of manipulation was needed to reproduce the subsurface heat transport. Yeah, so thank you very much for having me. Thanks for listening.